It is the night of May 29th, 1832. A 20-year-old boy sits alone in a room in Paris, frantically scribbling mathematical equations by candlelight. He is scheduled to fight a duel at dawn. At one point, he leaves a rushed margin note beside a half-finished proof. There is something to complete in this demonstration. I have no time. Those scattered pages will sit untouched for over a decade. When they are finally decoded, they will provide the foundation for modern abstract algebra. This is Évariste Galois. In less than 24 hours, he will be dead. The violent pressure of his impending death forced him to condense a lifetime of theoretical insight into a single sleepless night. To understand what Galois was rushing to write down, look at this timeline of polynomial equations. For centuries, mathematicians had formulas to resolve polynomials up to the fourth degree, represented here by these resolving shapes. But the quintic equation, x to the fifth power, was a brick wall. No one could find a general formula to solve it. Scholars like Paolo Ruffini and Niels Henrik Abel proved a paradox. A general formula for the quintic actually doesn't exist, yet specific quintics like x to the fifth minus 1 resolve perfectly. The mathematical world was stuck on a specific question. What is the hidden rule governing which equations can be solved by basic algebra and which cannot? Galois entered this world unsuited for its rules. Raised by a classically educated mother, he arrived at the rigid Lycée Louis-le-Grand in Paris and found the strict memorization unbearable. At 15, he discovered advanced mathematics. He read dense analytical texts by Legendre and Lagrange, the way other teenagers read novels. He began solving massive algebraic problems entirely in his head, refusing to write down intermediate steps. Skipping the manual arithmetic meant his brain was constantly looking for the underlying structure of a problem, rather than calculating the raw numbers. It was a brilliant way to think, but it made him incompatible with the French academic system. His sole ambition was to enter the École Polytechnique, the epicenter of French science, and a hotbed for Republican radicals. But his refusal to show his work on the entrance exam resulted in immediate failure. Days later, a local priest orchestrated a smear campaign against his father, driving him to suicide. Grieving and furious, Galois sat for his final attempt at the Polytechnic exam. When an examiner demanded a simplistic explanation for a basic arithmetic theory, Galois snapped. He threw a chalkboard eraser directly at the examiner's head. He was permanently rejected. Locked out of the academic elite, he was forced to pursue his theories as an outsider, detached from traditional mathematical conventions. This diagram shows what Galois realized at just 17 years old. Instead of trying to calculate the numerical values of the quintic equation, he looked at the geometry of its solutions, represented by these 5 glowing points. He noticed that you could swap these points around in specific ways, permutations, without breaking the algebraic relationships between them. He gathered these valid swaps together and named the collection a group.
Galois demonstrated that the complexity of the root landscape on the left is mirrored exactly by the organizational hierarchy of these symmetries on the right. This direct correspondence is what we now call the Galois connection. Because the group structure and the roots are tied together, solving an equation becomes a matter of dismantling its group. If that group can be broken down into a series of simple, nested components, the equation is solvable. If it is too complex to be dismantled, the quintic wall remains standing. He solved the quintic puzzle by inventing an entirely new mathematical language. He shifted the focus of mathematics away from finding numerical values, directing it toward mapping the hidden symmetries of structures, but nobody understood it. He submitted his paper to the Academy of Sciences. It was handed to the powerful secretary, Joseph Fourier, who died weeks later, leaving Galois' manuscript buried and unread in his office. Frustrated, Galois threw himself into the July Revolution of 1830. When his school locked the students inside to prevent them from protesting, he published a furious letter and was expelled. He immediately joined an underground Republican militia. At a banquet, he raised a glass to the new King Louis Philippe while holding a drawn dagger. He was arrested for the threat, acquitted, and then arrested again on Bastille Day for wearing an illegal militia uniform. He spent 6 months in Sainte-Pélagie prison. While sick in a cell, he received word from the Academy. The mathematician Poisson had reviewed a version of his manuscript and rejected it, calling his arguments unclear and impossible to verify. The academic gatekeepers lacked the vocabulary to comprehend his structural theories, mirroring a state apparatus that refused to tolerate his radical politics. He was isolated. In the spring of 1832, a cholera outbreak prompted authorities to move Galois to a medical clinic. There, he fell into a brief romantic affair with the physician's daughter, leading to a fatal dispute with a fellow Republican. On the morning of May 30th, Galois faced his opponent at 25 paces. He was shot in the stomach, abandoned in a field, and found hours later by a passing farmer. He died of peritonitis the next day. As he lay dying, he turned to his younger brother and said, "Don't cry, Alfred. I need all my courage to die at 20. A single musket ball erased a mind that had just unlocked the fundamental study of symmetry, cut short over a grievance that history barely remembers. His rushed manuscripts survived. In 1843, mathematician Joseph Liouville finally recognized their depth, organizing and publishing them to a stunned academic world. Galois had provided the tools needed to transition the field from classical algebra, the manual calculation of quantities, into modern abstract algebra, the study of pure mathematical structures. He was given 20 years. But the language of group theory he frantically scribbled down is now the tool we use to describe the fundamental symmetries of subatomic particles and the security of global encryption.